Good afternoon to all. And as I told you that energy and energy materials are very, very important. We are going to talk more on energy as well as energy storage devices. Basically, our area. I would like to introduce first our organization because I am the head of our 3 laboratories. So I have to do that at least what we are doing in all different laboratories. So. Yeah. So we have 3 laboratories. One is here in Pune laboratory. We are working on high purity materials. Then electronics for electronic materials for space applications and for DRDO. Then in the future laboratory, all kind of organic polymers, glasses, specialty glasses, all kind of things we do here. And in future laboratory we work on electroceramics because ceramics are used in electronics. Most of the ceramics are like alumina substrates, aluminum nitrate substrate, gallium nitrate substrate, and then silicon nitrate. All these things we work on. Then sensor is a big program we are working on in this future laboratories in Kerala. And high purity metals and alloys, it's a metallurgy related laboratory we have in Hyderabad. We work for high purity metals from 99.99 3N purity to 12N purity, 99.99 12 times. So these metals are required in space solar DRDO also, and some of our electronic applications like germanium we need in iron detectors. So we have 7N purity to 9N purity germanium we supply to SSPM. Then we have gallium also for 99.99 5N to 7N purity. Then zinc recently we developed 12N purity, which is required for the electronics as well as the DRDO. So we are supplying also small kgs to them for our national purpose. And different kind of alloys we require, like in space we require hafnium, zirconia and titanium alloys for nozzle with the propellant, the rocket. That nozzle is made up of the alloy of zirconia, titanium and hafnium. So we produce hafnium 320 kg in a year and we are supplying. So all these laboratories well set for different areas where we also work for everywhere some nanometal alloys, nano ceramics, as well as nanostructured other materials. So we have this center of excellences, these rechargeable batteries and technologies we have in Pune and additive manufacturing, these 3D printing technologies. Why rechargeable batteries are required? Because in future we have today the lead acid battery technology, and which cannot be utilized at least for 3-wheeler, 4-wheelers because the efficiency of the batteries is very, very low. So we are talking about lithium-ion battery technology, and this now materials and design everything with it, and we run the battery within the 2-wheelers with our own materials and batteries. And then future technology like sodium-ion battery, potassium-ion battery, lithium-sulfur batteries. This work is also in progress so that we can have the next generation battery. So, and in this center of excellences, industries along with us so that we can do something so it goes to industry. Then additive manufacturing 3D printing technology, at least small electronic component, whether we can do in 3D printing. Like it's better, like I told you, like zinc, 12N purity zinc. When we want to make some circuits and all this, whether we can do 3D print technology. Then 3D printed batteries, whether we can do. Because as you know, 3D printers are now very well known. You might have seen that most of the in Korean and in Chinese people, they have made flats in 24 hours with this 3D printing technology. So they can design on the computer, and same design flats can be made within 24 hours of around 500 square feet within 24 hours. The beauty of this 3D printing is we can have the walls with state of art, means anything on the statues or any other color combination, everything we can do with this 3D printing technology. So, and these technologies will have the very important in the e-vehicles also, because and other vehicles, automobiles, because the automobile, small automobile parts, where is the service station is there, they don't have to bother about from the company. They can have the 3D printer and they can make these small systems. So that is the advantage. The advantage of 3D printing is that suppose I want to make 100 numbers of atom or 1 number of atoms. There is no much change in their cost. So that is the one advantage. So we are taking care of all photonics, electronics with this 3D printing. Then e-waste recycling management. E-waste is e-waste recycling is very important, because today we have so much e-waste is generated. If you don't do anything today, so after 10 years, 15, there will be mountains of e-waste. So we have developed technology for e-waste recycling. We can recycle plastics, we can recycle metals, because in e-waste, if you process 1 ton of waste, PCBs and other things, it gives 150 grams of gold, 500 grams of silver, 5 kgs of copper. So all these precious metal, so now what is happening, people are sending it to Germany or something like that at 50 paisa per kg, this e-waste, and earn money. So now we have stopped that. So now we have technology, so we can recover gold, silver and precious metal and do that. So we have a laboratory we have a process plant in Hyderabad, where we work on this e-waste recycling. We have a 300 kg pilot plant demonstration, where we can we have transfer the technology to industry also. We have IoT sensors. So we have sensor center of excellence in sensors, where materials to sensors. So we do. So their IoT is also important. So including biomedical sensors, biosensors, then other gas sensor, pressure sensor, proximity sensor, magnetic sensor, everything we do under this umbrella. So there are 10 industries are already involved in these IoT sensors. So research, R&D, and further the manufacturing of this. So all these are taking place in this laboratory. So we have these very state-of-art areas where we have nanomaterials and devices. These nanomaterials and devices mean all nanomaterials are all in all these programs we use this. Then integrated electronic packaging, where our house was working, where is very important area. We have 2,000 square feet area where we can do the electronic packaging. So any device has to be packed nicely with good efficiency. Then there are some multi-layers or multi-circuits components, whether we can join together and make a compact device. So this facility we are doing that. So this facility, first facility was established in the country in Pune, where we used to give services to ISRO and DRDO. Now DRDO also have come up with this electronic packaging system, where this low temperature co-ceramic system. Then ultra high purity materials and semiconductor in Hyderabad. Then piezo sensors and actuators, all this in Trichy laboratory. Then metals for renewable energy. Under this we have solar cell, fuel cells technology. Then we have hydrogen technology. Then there from materials to devices we work here. Then battery, supercapacitor, all these things we work in under this umbrella. So This very huge, this very vast area. So we are going to talk much more on this topic. Then we have two national programs. One is the Graphene Innovation Center. So we have we can make graphene in large quantities. I mean, we have a reactor system of 100 grams scale, 20 to 100 grams scale we can have, and we are looking for the application of graphene in large, sensors and supercapacitor batteries, or other for photonic applications, like transparent graphene whether we can use in photonic applications. So all these things we include here. Then quantum materials technology. Since quantum computing is coming up, so where qubit and other things, so see the computers will be very fast, and there we need 2D materials like topological insulators, prisms, then the thermoelectric materials, 2D materials. So that we are going to have good facility in this center, and both the centers have the industry along with them, so that anything comes out, we can immediately transfer the technologies. So it's very important that how these materials technologies are important. As I told you, the energy generation, energy storage, sensors, all these are materials dependent technology. So sensor sensitivity is the materials property. So where the resistivity or conductivity of the material is important. In the solar cell, how we can make the material porous or make the material very transparent. All these things are very, very important. So these technologies, the materials technologies, we are making use of this, and we have a state-of-art processing facility. We can synthesize it, and in Pune laboratory we have LTCC-based development materials and nanomaterials alloys, glass and polymer nanocomposites. The nanomaterials in glass and nanomaterials in polymers have state-of-art other properties that we do. Then other renewable energy like hydrogen generation under natural sunlight. The good source is water, so we utilize water and H2S, these two sources we use, and we have developed hydrogen. So I'm going to talk more on hydrogen because there's very new things and very exciting some results I have, so I can talk more on this. Then thin film solar cells, we have good facility on thin film solar cells. So we can make quantum dot solar cells. Silicon quantum dots, now we are using the facility. Dye-sensitized solar cells, we are already making it. And we are improving with the dye and some other materials. And then energy storage materials and devices, we have lithium-ion battery and materials, sodium-ion battery and materials, flexible batteries and material batteries. Flexible batteries we started 3 years back, and we are coming up with some of the flexible batteries. Because flexible batteries are important, the next generation devices are flexible devices. Like today, you see the mobile today, it's a plain mobile, but after 4 or 5 years, we can have a mobile like a pen, whether it can be folded, rollable mobiles and rollable TVs, so we can put it on desk of your vehicle and go anywhere and see the TV. So this kind of, then the vehicles will come after 20 years, the foldable vehicles. So there will be parking problems. So foldable vehicles means we can fold the vehicle and hang, something like that. So these kind of things will come in the future. So flexible batteries are important. So we started working with flexible batteries, and we have come up with some of the solutions. Metal air batteries are very much required because the today ion batteries, lithium-ion batteries have capability to have 100 milliamperes, but if metal air batteries can be developed like aluminum air or lithium air or sodium air, they have 5 times more capacity. So there are some problems we need to solve. Then sensors, we have gas sensor, LTCC based pressure sensors, magnetic sensors. And for agriculture, we are talking about NPK sensors because these are very, very important today for the farmers. Then materials for strategic sector like thermoelectric materials and radiation shielding. So we have the quantum dot materials, quantum materials, where we can very small amount of the nanomaterials can shield the radiation, as well as the thermoelectric materials, which we can have both energy generation as well as cooling effect. Seebeck effect, through Seebeck effect we can have the energy generation, and for the Peltier effect we can have cooling effect. So both the materials we are working, because cooling effect is also very, very important for us. So small coolers can be developed with these materials. When we can give the voltage to these materials, then other end we can get the cooling effect of these materials. So this is the materials technology again. So we need to work more on the efficiency of these materials, whether we can have combination, whether we can have composites, ceramic composites. So all these things needs to be work on it. So we have a research innovation, then material development, prototype, and industry projects. Most of the research we are now trying to commercialize it for the public, and now we have almost 19 technologies are ready, and 10 technologies are already marketed, and they are on the rolling newspapers, rolling advertisement, so anybody can take these technologies. So this is the facility we have. This is the one reactor system. We can have nanometers at large scale. This is LTCC, like low temperature copacetic packaging, electronic packaging system, where it is the clean room of 10,000 class. Under that we have all equipments around. This is battery facility. We can make cylindrical cell as well as pouch cells, everything we do. We have glass making facility, because these are the specialty glass we do. And this is again we can make button cells, pouch cells. Then the glasses we can large scale. Then we have fuel cell technology. Then solar cells and sensors. So it's a typical material synthesis product, synthesis facility as well as prototyping facility. Both we have. This is in Trishul laboratory. You can see that we have the temperature sensors. With all kind of temperature sensors we do. Then using this temperature sensor, we have made one breast cancer detection unit, very wearable one. It contains all these temperature sensors. Their accuracy is so high. What they do, they just map the temperature of the body, and wherever when there are the cancer cells, they are red cells, their temperature is low. So wherever there are patches, so they just map it, and early detection of cancer can be done with this very simple technique. So this technology is also in the market. Then we have a supercapacitor. So we can make supercapacitor from 220 farad to 500 farads, and this technology is ready. So what is the beauty of that? We have the carbon aerogel production facility, because carbon aerosols are required in the supercapacitor. In supercapacitor, the major material uses carbon, which should have the surface area almost more than 1,000 meters per gram. So we are doing that. Then we have micro substrates, micro absorber, also the micro substrates for the piezoelectric components, piezo actuators. All this we work as a ceramic material, all dielectric ones, and from 2 to almost 14 dielectric, up to dielectric constant 14, we are making the ceramics. And these other, the automotive temperature sensor, pressure sensor we developed, we made some devices out of it. And this is a Hyderabad laboratory where we work on high purity metals, metal alloys, and we have this enable accreditation, as well as we have night vision camera materials and all these things we do there. Then this is a Hopmium plant also there here. Then waste recycling, we have e-waste recycling. Then we have done NAVEC antenna for replacement for GPS. Then we have silicon carbide crystals. Silicon carbide wafers are required in the e-vehicle. So this is now this is future market. So we have a single piece, this facility we have in Hyderabad. So we are going to make now 2-inch diameter to almost 4-inch diameter silicon carbide wafers in the. So it's a good project. And then e-waste recycling technologies. Now in e-waste recycling, we are doing PCBs. Then we also started battery recycling. So we can recycle batteries with metal, then cathode, anode, and lithium basically. So lithium extraction we do for batteries. Then solar panels. Many solar panels we are using for solar cell this activity, whether this solar cell panel also can be recycled. So we do recycling of solar panels. So all these things, recycling business we do in Hyderabad because that was the mandate given to us by the ministry. So what is there in the energy generation and energy storage? We are going to talk like the energy generation. We have a solar cell. Solar cell, you know that light energy converted into electrical energy. Then fuel cell. With fuel cell, we need an input as a hydrogen. This fuel cell technology like SFC is well mature technology. Now we need a very cheaper hydrogen to use fuel cells, so we can run the buses, trucks using the fuel cells. So making very cheaper hydrogen, highly pure hydrogen is important. Then wind energy, and then next is thermoelectric. I told you that thermoelectric energy generation with CMEC effect, whether we can have that. And this using these PJT materials like we can have the pressure on the materials and we get the electricity to these materials, that PJT. Also we are going to work on it. So we have come up the place like where we have come up the stage where some of the materials can give good wattage and all these things. So, but further we need to work on it. Then supercapacitor, battery, and hybrid batteries. So I told you that supercapacitor has a high power density and low energy density. So supercapacitor can be charged fast and discharged also fast. So maybe 10 seconds there is a charging and 10 seconds the discharging. Within a fraction of a second we can use you generate huge amount of energy, but it has to be utilized. So like in starter, we are using supercapacitor. There we need a very high power. But energy density is low, not as for the battery. So you have a lot of power can be generated, but needs to be stored. Then battery. Battery energy density is much higher as compared to supercapacitor, but power density is low. So we cannot run very big vehicles on battery due to the energy density of whether due to the power density or low power density of the batteries. So we are thinking whether we can have the combination of it. So we can have supercapacitor and battery together and make a hybrid energy device. Whether we can have little more power density and more good energy density, so that we can run vehicle or bigger vehicles or heavy load vehicles on these hybrid systems that like people are talking about railways. So whether this railways can be done, railways can be run on these hybrid batteries, because railways after half an hour or 1 hour there is a station. At the station we can have when it stops we can have a charging station. So automatically get charged, and so that can be done throughout the route. So this is one of the applications we are looking for. So all kind of nanostructures we do for the solar cells applications, like we have a doped MOH2. You see, this MOH2 is a highly porous and it's honeycomb-like structure. You see this honeycomb-like structure. Making such kind of structures is quite difficult. So we made bilayer and monolayer of MOH2. You know, these MOH2s are shows metallic properties when it has multi-layer stacking. So we need a semiconducting property. So MOH2 of single layer or bilayer is very important. Then we thought that whether we can have combination of both. Then we developed new material, CDMO also. It's a new compound we made. In this new compound, the band gap is very in the visible region. And this another component we have invented is a cadmium indium sulfide. It's again a new material. The beauty of this material is we can make this kind of flower kind of structure. We can make nanotubes. We can make also nanowires. So we started using this in solar cells, and we can tune the band gap in the visible. In solar cell, what happens? You need the band gap in the visible region so that maximum energy, maximum sunlight can be get absorbed, and more electron hole pairs can be generated to have the good efficiency of this material. So this is very important. So then we have quantum dots of cadmium sulfide based materials, cadmium sulfide, cadmium selenide, Ag2S, SNS2, and this we have made a thin film solar cells. We are getting almost 5-10% efficiency, but still we need to do stacking and all these things are not done yet. Then fuel cell technology we have made 188 watt PM fuel cell. What we need here the electrocatalyst like platinum. Now we are using platinum, so whether we can reduce the cost of this platinum by replacing this platinum with something else. So we did the combination of things and we have made a very cheaper fuel cell small prototype model. So this is our nanostructure of palladium and nickel and PT nickel, cobalt nickel. So all we did this in this, our laboratory. So this is another. So we need a very long some of the materials in large scale nanomaterials, like aluminum nano powder, aluminum nitride powder is required in the microelectronics, high power electronics substrate. Like there is a demand for ISRO as well as demand because they need these aluminum nitride substrates as part of high power electronics. So this is we made with this our equipment. This is 100 grams per hour scale. We can make with this plasma reactor system. What is the plasma reactor? This is a plasma actually. So your material itself as a cathode, work as a cathode, and this temperature goes to 3000 degrees centigrade. This alumina get vaporized, and then we can add nitrogen and ammonia along with that and quench this aluminum nitride powder in this glow box. So we get very 50 to 100 nanometer scale powder. We can also make copper, aluminum. This is aluminum nanopowder of 50 to 100 nanometer scale. We can make in large quantities. And aluminum nitride, you can say 500 gram in 2 hours. So, and these copper nanopowders we need for the propellant. The efficiency of the propellant means oxidation of the propellant can be enhanced with this copper or aluminum. If you have a nano size, then the efficiency is much more. So we need to use very small amount of copper or aluminum as compared to micron size, and we supply with this supply to our DSU and HMRL laboratory in Pune as well as ISRO for investigation. So next generation energy. Next generation energy is the hydrogen. Why is hydrogen is important? Because The calorific value of hydrogen is much higher as compared to fossil fuel. So it's almost 3 times more than the petrol. So a small amount of hydrogen can give large amount of energy. So that has to be considering that whether we can have a hydrogen engine or we can have a hydrogen storage systems. What we can do, we can have very highly porous solids. In the highly porous solids, we can press the hydrogen. This hydrogen is covalently bonded with this material, and at low temperature, just giving 50-degree temperature, we can that can release the hydrogen. So whenever we require hydrogen, we can do that. So this can be useful for two-wheelers. Then it can be useful also for electronic systems and all these things. So that considering that we are talking that whether we can have the cheaper hydrogen. So this hydrogen can be utilized for fuel cells, then as a directly hydrogen for hydrogen. If you have hydrogen engine, then we can whether we can use electrolytic hydrogen, all these things, and then photosynthesis. All these things are matters. All these processes whether we can do, and we can have this the hydrogen, pure hydrogen for this fuel cell, as well as a direct pure hydrogen for any for the hydrogen engine. So our we are talking about the many processes of this hydrogen, whether we can make cheaper hydrogen out of it. This is the standard method of making hydrogen. This is steam reforming method. In the steam reforming method, you see the methane is get oxidized, and it's a very highly endothermic reaction. You see 206 kilojoules per mole, and lot of this, it happens at some 800 degree temperature, degree centigrade, and CO and hydrogen is produced. The problem here is how to get rid of CO, or how to the CO2 is also generated, CO plus CO2 and then hydrogen. So separation of CO2, CO and hydrogen is much more complicated in this process. So people are also talking about hydrogen from biomass, but it's again a very slow process. So very slow process. So whether we can, and slow process as well as along with hydrogen also we are generating CO2. So again the separation is a problem. So it has this process has two drawbacks. Then electrolysis of water. It's a very simple process. Just electrolysis, just give some voltage to some have some cathode and and give some voltage, so we can at cathode we get the hydrogen and anode we get oxygen. So this we get a very high pure hydrogen and oxygen, but there's a lot of energy has to be given for this electrolysis process, and quite expensive. So however, though it is expensive, but we need to see how we can make this process much more simpler and economically viable to produce hydrogen. Then we thought that whether there are other sources for hydrogen production of hydrogen. So we see that H2S is lot of H2S is generated in the refineries, as well as in the municipal water and all this. Whether we can use this H2S and produce hydrogen along with that. Now, at the moment, what they are in the Claus process, this H2S get oxidized and form liquid sulfur, because liquid sulfur is required for the fertilizer industries. Our all fertilizer industries depend upon this Claus process, because they need the sulfur for the fertilizer. So, but this process again a very, very complicated process. 730 degrees in nickel alumina catalyst, high temperature, and highly corrosive and energy intensive. See the H2 here what happens because of this high temperature and sulfur, you have to be very careful about the design of the reactor system, and because every time this reactor system has to be changed, because the sulfur gets sulfur just corrodes the metals and other parts. So Another process we are talking today is whether we can have a photocatalytic process. Because see, the water splitting is how much energy will require. Like delta G is around 237 kilojoules per mole. It's highly positive, and electropotential is 1.23 electron volt. It's much higher as compared to H2S is very small. We need only 33.44 kilojoules of energy to break H2S, and here the electropotential is only 0.17 electron volt. So it's much easy to split H2S as compared to water. Water needs a high amount of energy because it's you can see the free energy is a lot of endothermic in nature. So what is happening in the photocatalytic process? It's a very simple process we do at room temperature. All these semiconductors have the tendency to absorb the light. Okay, absorb the light, and then there is a photoexcited. Electron holes are generated, and there is a tendency of electron holes, they get excited, they go to valence band, conduction band, and the recombination process is a natural process. Okay, so whether we can stop this recombination process and increase the free electron or free hole. And these free electrons are responsible for reduction, and free holes are responsible for oxidation. So suppose I want to utilize this as a catalyst for photocatalyst for any water spreading. What I need to do, I need to suppress the holes. As soon as electron holes are generated, just try to suppress the hole and more give the more free electrons process. And these pure electrons, if they are very highly energetic, they start reacting with water and produce hydrogen and oxygen. So this is actually the basic process of. It is not normal catalytic process. Normal catalytic process is a highly reactive process, which is reacting with the material and again regenerating. Okay. So catalysts may not be taking part reaction, but catalyst sites are very important. Active sites are important. In here, photoexcitation is also important. Then how you can stop, how you can enhance the how you can stop the recombination process. That is also very important. So while designing material, which we can have the semiconductor which can absorb maximum sunlight, means their band gap should be well within the visible region. So it should cover from little near UV to almost IR. So the spectrum of total sunlight, if we can cover, and then it can produce maximum charge carriers. And whether during between that, whether we can use some reagent, we can capture the holes or capture the electrons. So these things are very important. And then, considering this process, we develop good catalyst for that highly efficient catalyst. See here at room temperature is a water. We can have catalyst. This is a natural sunlight which absorbs the natural sunlight by this catalyst. It's a semiconductor. Then the photoexcitation takes place. Electrons, holes are generated inside, right? Then we can trap holes during this process, and the electrons are free electrons are responsible for the reduction of water. So this is a very important process, and so design of photocatalyst very important, like tuning of band gap. Then we can have a sulfide semiconductor, we can have oxide semiconductor, we can have nanostructure materials. See why you want to the nanostructure material also very important here. When we are nanostructuring it, there are a lot of defects are formed, and the defects are responsible for to suppress the recombination of charge carriers. So nanostructuring also get help. Like if you have quantum dot kind of thing, when your size is very near to your bore radius, definitely that helps a lot in such kind of process. This is already explained, I will not go for this. This is the simple reactor system. This is artificial our xenon lamp where we can have whole spectrum of, maybe then we can have the top of the here. Laboratory we have one reactor system which can produce, this is H2S, it is water system, H2S as well as water we can split here. Here also we can do both the thing under natural sunlight. So this is the first system we developed. You see the nanocrystals, nanowires, and self-present cadmium lanthanum sulfide. What is the beauty of this structure? You see the all hexagon cell assembled in the one, and they are highly porous. And they are highly crystalline. Because of this, and their band gap is in well visible region. See the absorption is within the visible region. So it shows good photographic activity. And we, since it's a new catalyst, we did some simulation of. Then end of ZnW4. These are the latest things we like. ZnW4 is a band gap in the very UV region. You see, okay. Here their absorption is 375. When we dope with nitrogen, their absorption is increased in the visible region. Why we have selected ZnW? It's a highly stable compound. It's a highly stable compound, and we found that this is one of the good ZnW4 nanorods. On the nanorods, in between the nanorods, we have small nanoparticles and some pores on these nanorods that help a lot. While when as soon as you dope nitrogen, so these rods get distorted and porous, and that also help a lot for getting the good hydrogen production. You see, with the pure nitrogen doped hydrogen, ZnW good photocatalytic activity. Then. As you know, neobium also very good. Neobium oxide is highly stable compound. So, considering our commercial approach, we thought that whether we can use such kind of thing and do their absorption in the visible region, and we are successful in that. Then SN304 is one of the good photocatalysts. The beauty of the SN304, we can have nanoplates, we can have nanorods, we can have nanowires, and doped with nitrogen. That gives a good photocatalytic activity. Like here, you see, there is a great enhancement through the nitrogen doping in the water splitting process. See, another is the tantalum oxide, because tantalum, like niobium oxide, tantalum oxide is a very highly stable compound. And we could produce gamma tantalum oxynitrate. With nitrogen doping, see, tantalum oxide is a white color compound, means it is in a visible UV region. If you will slowly dope with nitrogen content, you can take that color from yellowish to almost dark red. So that much nitrogen doping if you could able to do, so we can get the whole spectrum of the visible light. As I discussed with you that MOH2 and CDMOH4, this is basic structure we got it in MOH2. When we have CDMOH4, CDS combination of CDS and MOH2, we get a very porous structure, and this help a lot to get a good photocatalytic activity in the for water splitting. See, then this is you see here the CDS alone give only 10320. Okay. But with the MOH2 12,000, this is 12,000 to 5 is almost 500 ml per hour, and this CDMS for much more than 1 liter per hour. So this kind of enhancement is observed. So we got very good publication on it, like almost the JMCA. We explain how these structures are important for the hydrogen production. Then we did a core shell. So we thought that whether we can MOH2. On the MOH2 we have CDS, small thin layer of CDS, and we found that it also works very well when we have core shell. We get good, almost 35% quantum unit. Then Since it's a combination, see in electronics and this is the beauty of material science. See, when you have heterostructures, we have core shell structures. They give different properties. Like heterostructure, means you have two, like cadmium sulfide is one of the visible, the band gap is within the well visible region, TiO2 in near to UV. When we have a combination of both, then the heterostructure means at the surface, at the interface, we can get the recombination, suppressed recombination, and that helps a lot for getting good hydrogen evolution. So this is again ZnW for CDSO. I will not go in details. And this is again Zn ion place for new compound we have formed. And this is a new compound with the SiO2 layer gets good hydrogen production. And this SNS is a good visible light component, and this semiconductor, and Zn92S4 is a visible light good absorption. So we thought that whether there is anything happens at the interface, and we can get the suppression in the electron recombination. And we found that there is a great enhancement in the hydrogen production from here, from 650 to 6 almost 100 ml to almost 200, 300 ml per hour. So this combination, really helps to, since it is a electronic process, so this combination it helps a lot for getting hydrogen evolution. Then one more new things we did, whether instead of having inorganic components, whether we can have organic molecules. So this is organic molecule, 613 pentacynol, and this we coupled with TiO2, and we found that when we have a decoration of TiO2 on this nanoplates of pentacynol, there is a great enhancement in the hydrogen evolution. The maximum hydrogen evolution, like 36,400 microvolt, means almost 2 liters to 2.5 liters per hour we got with this system. So we publish in JMCA. So good, we have got very good citation for this paper, and we are thinking whether, but being organic, their stability is very low. So whether we can enhance the stability, or whether we can modify this molecule. So that's things our students are working on it. Then we have some nanostructures like this. So we have made all nanostructures, and to see whether we can get very stable compound, like nanocuboids, then this kind of nanorods and all this. We studied all kind of shapes and all these things, and we found that a spherical type of nanotube kind of structure or graphene structure can give better results. Then quantum dots, like very, very important. Like when you have like CDSSC, cadmium sulfide, they are well in the visible region. And then is like CDSSC, Bohr IDC is 5.6 nanometer. If you can synthesize the CDSSC in the range of 5.6 nanometers, it's called as quantum dot size. So we can have 2 nanometers to 6.55 nanometers. We can have all colors. This is quantum dot star. Now they'll be usefully in the LEDs, so that whether we can have a stable quantum dots, because we can have the size and we can have this all colors in the one compound. This work is already going on. Whether we can have in polymer, we can have glasses. So this is typical materials glasses. So we have CDS quantum dots in glasses, CDS-AC quantum dots in glasses, CDC quantum dots, bismuth sulfide, bismuth telluride, then bismuth quantum dots. Whether this kind of very low size materials can be grown in the 1300 degrees centigrade. What we have to do, we have to select design the composition of glass. In this glass, we can grow cadmium sulfide quantum dot. So there is a low thermal, thermal processing from 500 degree to 625 degrees centigrade with control manner, and we can see here we can grow cadmium sulfide. You can see the band gap can be increased from so here the absorption, initially it is a UV region. When you grow CDS, it goes to the visible region. So this kind of things is very, very important in the glasses. And you could spectroscopy, PM, you can see the transmission electron microscopy, this isolated cadmium sulfide quantum dots are seen. This is only 2.5 nanometers or 2 to 3 nanometer scale, and they are uniformly dispersed in the glass, And beauty of this, they are polycrystalline. So you can see the very highly crystalline series can be grown in the glasses. Very typical. Typically, you can see that this may be 2 nanometer, this may be 5 nanometer, 6 nanometer, and 7 nanometers of cadmium sulfide. So with size, we can control the optical properties. And this is very typical cadmium selenide glass, where we can have developed some quantum dots of 5 to 7 nanometers, 4 to 5 nanometers. Very close, their narrow distribution means they don't go beyond 5 nanometers. So this absorption shows, very steep absorption shows the size of these quantum dots are very uniform. If their absorption is very broad, then it shows that some of the 2 nanometers, some of the 3 nanometers, 4 nanometers. But being a series, 5 nanometer of this quantum dot are uniformly dispersed in the matrix, where the absorption cutoff is 575 nanometer. So this is CDS, that was CDS and CDSC also we developed. They have the cutoff is around 710 nanometer. It is almost in the near IR region. So this glass can absorb from near UV to almost near IR region the light, which will be helpful for our photocatalytic purpose. So you will see this very 6 to 8 nanometer CDSC in the glass, very uniformly dispersed. And see here, initially it may be very colorless, but as you give the treatment to the glass, inside cadmium sulfide or cadmium selenide will go in the glasses and form this color, means these their optical properties get changed. And that, considering this, we thought that whether this can be utilized for the hydrogen production for the first time. So we have taken US patent on this for this hydrogen production. So this is a cadmium sulfide quantum dot glass. You can see the almost the particle size is 3 to 4 nanometers here, which gives the much higher hydrogen evolution, 554, and the sample which we get here, 0.5 gram of glass, which contain hardly 0.005 grams of cadmium sulfide. So a very small amount of quantum dots can give large amount of hydrogen. This we have shown, like nanowires we develop in the glasses. This is the CDSC nanowires. You see, very small one, 10 to 15 nanometers, 5 to 10 nanometer size nanowires we develop, and that also gives good catalytic activity, around C50. Here, only thing is how much nanowires we can produce. Means we can, suppose we can enhance the concentration of CDS and get more nanowire, definitely this will increase. So, and size, if you will go much more, 1 nanometer, 2 nanometer, the efficiency is much will be higher. So this again, we made Germanic glasses. Typically same, when initially silicate glasses, I thought that whether we can have low temperature. So low temperature glasses give much more effect here. Cadmium sulfide. Incidentally, what we happen that the cadmium sulfide which you dope, here we are getting orthorhombic of cadmium sulfide, which is not, it's a metastable state, but this metastable state is stable in the glass. So that was a new invention in this, and this metastable CDS is much more visibly active as compared to other cadmium sulfide. So this is the uniformity of particles, and then hydrogen evolution is much higher here as compared to earlier classes. Then we have a CDCC, this whole spectrum from 300 nanometer to 700 nanometer gets, we can tune with only the size. So this is the size of conduction effect. In the CDCC, we are getting it a very low, it's only 0.5%, so XID is very, very poor. So we supported with Raman and TM. See here, very low, where the quantum dot size is very, very low, 4 to 5 nanometer, we get high hydrogen evolution. So we feel that if we produce 3 to 4 nanometer or 2 to 3 nanometer, this will be enhanced much higher as compared to other. The beauty of this is the regeneration is very, very easy, because just put water, rinse it, and again put back for the catalytic purpose. So incidentally, instead of bismuth sulfide, we got bismuth, but since it is a metallic, so we found that metallic nanoparticle inside, and which gave a huge amount of hydrogen evolution, 11,541, very small amount. So this this we have taken the US patent of this catalyst. Then this here another the large scale results which I am sure that 11,002 particle size is 1 to 2 nanometer. You can see here. So which indicates that a very lower particles can give much better results. Then instead of sulfide, whether we can have EG3PO4 is a very, very well-known photocatalyst for hydrogen evolution. But problem of this EG3PO4, it is decomposed. When light falls on it, immediately silver and phosphate get separated. So we thought that whether we can grow in this glass, and we found that there is a good, we have grown this EG3PO4 and they are highly stable. You can see they are highly stable in the glass. Okay. And this we supported with Rama. Then you can see very important thing. This EG3PO4 has dodecahedron structure. And in glass also we found they have dodecahedron structure. So it's very, very microscopically also we can see that the dodecahedrons are conformed maybe 5 to 7 nanometers of dodecahedrons here we can see. This is a powder of EG3PO4. It's unstable. It can have 500 nanometer absorption here. So that hence the visible region, we thought that this powder we can make and immediately put it in glasses and heat treat these glasses, and we get absorption in the visible region. You can see it is the formation of EG3PO4. Why this has come? What happens during the process? This silver gets decomposed, and because of this silver we get so we thought that whether we can have excess PO4 and suppress this, and we did that. And we get the good hydrogen evolution also here. And this is our bigger reactor system, so we can produce 2 liters per hour hydrogen evolution system. So 45,000 micromole per hour. So we are in fact in the industry now, so whether we can commercialize this with water safety. Now we are talking in 2-3 weeks back, I was in Ladakh, Leh and Ladakh, whether we can have, because in Ladakh and Leh there is a lot of sunlight, so whether we can utilize these systems there. And anyway, oxygen is also less, whether we can produce oxygen, and hydrogen can be also utilized for heating system. So that is the good things we are planning, that whether we can put one reactor system there. Then another area we started the neutron energy is a very, very important topic. Now we started this project with German group, neutrino, Germany group neutrino. These neutrinos are coming from the sunlight, where there's, like we are sitting today here. So neutrinos are around us. Okay, and this neutrino has a mass. Now people are found that neutrino has a mass. When neutrino has a mass, then it has the energy. Whether we can capture this energy. So we are developing some materials. Whether this neutron energy capturing may not be directly captured. Whether if they are passing to the material, whether their energy is converted into kinetic energy, and see whether we can utilize that. What is the end application? We can have the materials with this like car made up of these materials, this neutrino capturing. So it doesn't require any other electricity. It gets automatically charged. So when you have car in park car in your parking place in the night, morning itself it will get charged. So this is the concept. With we have some prototype developed along with the German group. Some of the small things, if you stack them, suppose this one stack is 1.5 volt, we have 10 stacks, it gives 30 volt. So without any connection, so that is a great thing. So how to now convert for the commercial scale? That is great thing. We are working on it. Very soon we will have some good results. And our part is how to make 2D materials for them, because we found that 2D materials with a twisted graphene, or on the graphene there are quantum dots, isolation of quantum dots, isolated quantum dots for this system. So where this very nanoscale energy generated through this very small amount of generated through this neutrino, whether it can be captured by this material. So see, materials are very important today that can help a lot for energy generation and energy storage as well. So this is the new project we started. This is our center of excellence in batteries. What we do, we produce battery. In battery mechanism in batteries, we have one electrolyte. Any battery, one is anode, one is cathode, and one is electrolyte. Okay, electrolyte used for transport of ions, right? So this is the anode, this is the cathode. When we charge it, okay, when we charge this, some of the ions anode go to the cathode and sits here, and while discharging, they will again come back. This is the process. So charging and discharging one cycle. Today my battery has 1,000 cycles, so that it can run 1.5 years, or because one day we can charge with one cycle, right? So how to improve materials? So materials should have a layer structure. All these two materials, anode or cathode, they should have a layer structure. Why it is the layer structure is required? When ions get transferred from anode to cathode, it should sit here in the layers. Okay, so that more number of accommodation of ions in the layer structure gives maximum amount of storage, right? So we are developing cathode, anode of layer structure, so that we get maximum amount of energy storage. So we develop some new materials, new anodes. We are talking now today. We have silicon, then we have silicon quantum dots based graphene. Everything we are doing it. I'm not going to details on it because we have almost 20 students working on this as a research students. They are working on different topics. So see these. So anode is also important. Cathode is also important. Electrolyte also important. Why? Because when we are transporting ions, that should safely reach to the anode or safely reach to the cathode. They should not react in between. As soon as they start reacting in between, their reversibility goes down. Means your charging, discharging will come down, right? So you should have very safe electrolyte. So the ionic conductivity of electrolyte is almost into 10⁻³ order, so that the conductivity is much better. What is the current problem is, these all electrolytes are organic based electrolytes. Means all this like lithium and sodium get dissolved in electrolyte, organic solvent like dimethyl carbonate, ethyl carbonate, and one molar solution we put here. What happens when we charge the battery, the temperature goes up. If temperature goes up 60, 70 degrees centigrade, definitely this electrolyte vaporizes, and there is a swelling in these batteries. Then there will be some explosion. So we cannot charge the batteries. As soon as we charge the batteries very fast, the temperature goes in the battery is also very fast. So whether we can remove the organic, whether we can have a polymer electrolyte, whether we can have a solid ceramic electrolyte, whether we can have a glass electrolyte, or combination of others, or ionic liquid, organic liquids. There are some ionic liquids, temperature goes to 300 degrees centigrade, 400 degrees centigrade, the boiling temperature is more. Whether we can use that ionic liquids for this purpose. So all these 4 areas we are working, and we would like to settle that issue whether we can charge the batteries, because when I buy the car and at the charging station I have to stay for half an hour, I will not buy the electrical vehicle, right? So unless and until I get only 2 minutes charging at the charging station, so a common person can buy the electrical vehicle. So we developed this model, active material, means all cathode, anode, electrolyte we can develop. Okay. So one company can produce that only. Other company only coated electrodes. So we have to coat these electrodes here. This anode, which is aluminum, this is copper. On the aluminum we have anode material, copper, and only these electrodes they can make and supply to. Model is a cell assembly, means we can fabricate along using this electrode, just fabricate the cell assembly. What we are doing now, we are purchasing outside this one, single one. They may be 2 ampere. And now I want to make 48 volt battery, then this 2 ampere battery I can put it in series and put it in parallel and make any kind of capacity, any kind of voltage. So now we have this. So technology is available for this. So we are doing that. Cell electronic. So there are the facilities now we are developing. So we have a mobile battery. We have to replace this is the mobile with our own lithium-ion battery. This is our, I don't know whether I can run for you.
That sir, actually, I think you are having several phone calls. Several phone calls are coming.
So this is actually this is our own battery, 2-wheeler battery, also we made. And and this is again the other materials we are working on for enhancement of the capacity of the batteries. These are the nanostructure we are utilized for higher capacity. Now we are working on sodium ion. So we made a mobile battery of sodium ion. We have demonstrated last week in Digital India program. Prime Minister has inaugurated that. Then this is a flexible. We made a polymer electrolyte, and we have made a flexible battery out of it. That gives a good capacity. Then supercapacitors. So all kind of supercapacitor we make in research laboratory from 25 farad to almost farad. So we use 25 volt as well as 35 volt of module. This is for the EV pad battery, because this EV pad electronic voting machine, they are using batteries. So this to decrease the number of batteries, we use that. So these are the supercapacitors in all form we make. There is printed battery, which is additive manufacturing we are trying in our laboratory. So these are recently we developed this COVID-19 polymer sacks. Here in Bangalore company AEMD Additive Manufacturing Society, along with government. Then we have nanomaterial coated antiviral mask. That also technology we have given to some of them. And this is conclusion. So we can see that there are a variety of applications and variety of materials where we can work on. There are number of applications. You know, my hands are not. So this is the ocean we can see. So if you can, thank you very much. If you have any questions, you can. You can ask any question. No problem.
Why not use plastic for
Pardon?
plastic for
Oh, we can use it plastic for that. Recycling of plastic and produce hydrogen. That process again very expensive. Expensive. So if you want to do incineration or the temperature is around 200, 600, 700. Yeah, catalyst we are trying whether we can this plastic itself we can degrade at 100 degrees centigrade, 200 degrees centigrade. So we have given some startups from people. They are working on it for this with catalyst.
There are two methods. You can use plasma.
Yeah. Plasma again, expensive. Too much expensive.
But a lot of plastic is produced.
But plasma actually, at the moment, people are working on this plasma-based reactor system. But there, what happens? No, plasma comes. It will use all kind of only the metal polymers, and it directly burn as a carbon and metal embedded in that. The separation of this is again a big problem. So that things will happen. When that becomes then expensive.
Okay. I think,
Thank you.
very
Thank you very
informative,
much.
very useful we have our next.
So on behalf of University and our AEMD national seminar, especially thanks to Kale for his wonderful talk on a complete, I think it's covered, I think from what about the active material to the fabrication of the devices. Like that is very innovative information, we got it. Even I am working in the batteries for 20 years. Just now I noted down very interestingly, one or two important materials. We can dope with silicon oxide with some other hybrid materials, especially for neutron energy capturing. I think recently has developed with German technology. It's a very interesting, very beautiful. It is innovative technology for the next 1 decade. Thank you, sir. Thank you a lot. Once again, I thank.